All right, so we're on chapter 6. So we've gotten through the basics of, molecules, how they operate, some of the different laws associated with gases, and then all that stuff. So that was all a precursor to now the meat and potatoes of the whole, I guess the whole class is, refrigeration. How it all works, how it all ties together. So today we're going to explain the 4 main components of the refrigeration cycle. These are the 4 key items that you need to walk away with from this class. I don't care if you understand what Charles' law, Boyle's law is, or anything like that, but understand what the 4 main components of the HVAC system is, or the refrigeration system. We're going to identify whether components are on the high or low pressure side of the system, explain the function of the compressor and why it is the heart of the system, explain the role of a condenser and how it impacts the cooling cycle. And then we're going to identify additional components that may be found on a condenser side of a system and explain their roles. Describe the function and placement of a standard metering device. Metering devices are critical as they regulate the flow of refrigerant, and you're going to understand why. And we're going to learn about the evaporator. So let's get started. So refrigeration, all right. The purpose is to remove heat from a space where it is not wanted, and then we're putting it to a place where it makes no difference. So if we're talking about, let's just say, a refrigerator is going to take the heat that's inside there. We just put in a hot bowl of soup or whatever the case may be. The refrigerator is going to remove that heat via the refrigeration process to outside of the refrigerator, outside of that box. Your air conditioning system is then going to remove the heat from that soup to the outside, all right, where it really makes no difference. If we were to have a refrigerator constantly running and we're putting in hot soup in it all day long, well, we're not going to just remove the heat from the fridge to our home, because if we do that, now we're just transferring the heat and making our home uncomfortable. So we have to really remove that heat and put it to a place where it makes no difference. So that's the key point. Doesn't really mention it here in the slide, but that's something that we have to understand. All right, we can move heat from one place to another, but we also want to make sure that nothing else is really affected. So refrigerant acts like a sponge. All right, it's used to soak up and move heat. Not sure I really care for this illustration off to the right, but it's what the book really has. All right, it's basically refrigerant is going to act like a sponge inside of the system. It's going to absorb the heat as the refrigerant's running inside, and then it's going to come out to the outside and it's going to squeeze it out. All right, so it's basically our sponge is right here up at the top. It's ready to be filled up with heat. All right, the heat is absorbed as it passes through the cycle. Now we get to this point where our sponge is completely saturated with all that heat. We take it to the outside, we squeeze that sponge, the heat is released, and then we're back to repeat the process again. Okay.
The compression refrigeration cycle provides a means of cooling a conditioned space. Whether used for air conditioning or refrigeration, the system relies on 4 major components to transfer heat: the evaporator, the compressor, a condenser, and a metering device. The process begins at the evaporator, where air passes over the cooler surface of the evaporator coil. Since heat always moves from a warmer to a cooler place, the air gives up some of its heat to the cooler refrigerant flowing through the evaporator. This causes the refrigerant to change state from liquid to vapor. The superheated vapor refrigerant now travels to the compressor, a pump, which is the heart of the system. The compressor squeezes the refrigerant, raising the pressure and the temperature of the vapor as it pushes it to the condenser. The condenser is the heat rejection component of the refrigeration system. As air flows over the condenser, Heat from the refrigerant is transferred to the cooler outside air, causing the refrigerant to change state from vapor back to liquid. Although the refrigerant has given up heat to the air, it is still a high temperature, high pressure liquid as it leaves the condenser. A metering device provides a rapid drop in pressure and temperature, beginning the change from liquid to vapor as the refrigerant enters the evaporator, ready once again to absorb heat from the conditioned space.
So that was just a little bit of a video describing, what the process is like. Okay. So I usually like to start from the metering device. It's just good centralized location, especially for this illustration. Basically what we've got going on here is we've got a liquid, low pressure refrigerant coming through. It's at that point where it starts to absorb heat. As it starts to absorb heat, it starts to turn into a vapor. All right. This is that saturation, that saturated vapor. Basically, we're at that point where we can go one way or the other, sort of like the middle ground. As we get to the end here, we start to increase the temperature of the refrigerant. The heat is being absorbed. Going back to the compressor, compressor increases the pressure of it. By doing so, now it's a high pressure vapor. We remove the heat. As we remove the heat from it, it starts to liquefy or condense, and now we have a liquid, high pressure liquid coming back to the metering device, and we repeat the process. All right. The big thing is that we have to take away, it's the change of state of the refrigerant that allows for the absorption and the expulsion of this heat. All right. If we just had liquid refrigerant running through the entire system, we really wouldn't move the heat out of our home very well, all right, or at all, for that matter of fact. So we have to have the right amount of gas inside of our system, so we have to properly charge our systems to the point where we're going to have a change of state, going from a vapor to a liquid. Not enough refrigerant, we're always going to stay in a vapor state, and we're not going to be able to release the heat properly when that refrigerant goes to the outside, to the condenser. So we have a high side and a low side. We just illustrated in the in that little image there. The high pressure is a high temperature for heat rejection. Low pressure equals a low temperature for heat absorption. Okay. Low side, heat is absorbed into the system. High side, heat is rejected from the system. Compressor divides low side from the high side, and the metering device divides the high side from the low side. All right, just all the things that we really covered in that little illustration there. So what's the compressor? All right, the compressor is a pump. All right, it's moving that refrigerant through the system. When the compressor is not running, all that refrigerant equalizes. Okay, so I may have a high side and I have a low side. If the compressor is not running, everything is nice and equal at a balance. If I were to put my gauges on both sides, I should see almost no difference. Sometimes there's little small fluctuations with your gauges, but if it's 120 on the low side, compressor's not running, I'll get 120 on the high side. As soon as that compressor starts up, my high side is going to increase, my low side is going to decrease. All right, I've got a suction naturally forming on the low side as the compressor pulls in that refrigerant, and then on the high side, I've got that force. It's just pushing that refrigerant through, and we're just sort of feeding, one feeds the other. We've got that pushing expulsion force coming back to the low side, coming back into the suction, and just completing this giant circle. The compressor, it's known as the heart of the system. It separates the low side from the high side, creates the high pressure, creates the low pressure on the low side. All right. It's the most expensive and crucial part of the system. This is very, very true. There's a lot of mechanics, a lot of engineering that goes into a compressor. We need to ensure that it really stays healthy. All right, that means we're pulling the proper evacuation. before we charge that, okay? We'll cover that a little bit more in some later chapters, but an evacuation is just making sure that we're removing all the moisture and non-condensables that are in the line prior to filling the system up with refrigerant. I know I told you guys about this maybe a few weeks ago, but we want to make sure that there's no moisture in the system. The reason being is that we we don't want that moisture mixing with the refrigerant oil. If it does, it starts to create an acid, and when we have an acid, it starts to eat away at the motor windings inside the compressor. If that happens, we form a burnout, and now all of a sudden our entire system is contaminated, and we have this oily, sludgy acid eating away at everything inside. I can replace the compressor, but it's going to happen again if I don't clean out all that oil sludgy mix. So the best thing to do, make sure we pull a proper evacuation. We put a vacuum on our system. We suck out, or not suck out, well, partially, we suck out any impurities that are in the system. We also drop the pressure into a vacuum state. By doing so, we cause the moisture to evaporate, so we don't have that 212 degree boiling point anymore of water. We've got a sub-zero boiling point of water, and everything is just going to naturally boil out. We'll have a nice clean system where we can release the refrigerant and have less chance of a burnout. Okay. So if we do have a compressor that does fail, there's a lot of work that's involved as far as replacing it. Sometimes it's just much easier just to replace the entire condenser rather than deal with replacing just the compressor. In larger commercial settings, that's not really an option, so you will replace the compressor. And they are heavy, so just keep that in mind. We're talking about 100, 150 pounds a piece on average just for residential units. So we have the evaporator and the compressor. So just on the intake stroke, over here, the air, or the refrigerant I should say, gets sucked in. And the piston goes in a downward motion. It creates a vacuum or a suction force. Suction force creates a chamber that gets filled with refrigerant. As the stroke goes into an upward motion, it starts to compress all that refrigerant. As it compresses, the suction valve closes, and then the discharge valve opens at a certain pressure. Okay, it's not going to, if the piston's only halfway up, both these valves are going to be closed until the pressure releases or gets to a point where that discharge valve is going to open. All right. That whole compression cycle results in a high pressure vapor. When a system is operating, a discharge line becomes very hot. All right. Why is that? Well, if we go back to the previous slide, I've got friction and energy from this motion of the piston. As it goes upwards, the friction, the energy creates heat. All right. All these molecules are being jam-packed together. They don't like it too much, and the end result is going to be heat. So if I were to grab the line coming out of the condenser, which is the small little liquid line, I will feel a bunch of heat, and that won't feel too pleasant to the touch. So we have the condenser and the metering device. The condenser, temperature difference causes a release of heat. All right. So what we have is this refrigerant flowing through our piping inside the condenser. Okay, I've got that high pressure vapor that's just waiting to release all this heat. All right, refrigerant doesn't like being in this state. If we're talking about 410A with no pressure applied, 0%, 0 psi atmospheric, it wants to boil somewhere around -60. Okay, so it doesn't like keeping all this heat with it. So how do we release all this heat that's inside the refrigerant? Okay, the simplest way is we put a little fan on there. put a fan at the top of the condenser. That fan starts to spin. It sucks in air through the sides of the unit and dissipates all that heat going upward. So a neat little trick you guys can do at your own homes during the summertime, or maybe you've even noticed this. When your fan is running on your air conditioning system, if you take your hand and you put it over the top of the fan blade while it's running, you're going to feel a lot of heat coming from that. Well, that heat that you're feeling is all the heat that's inside your home being expelled to a place where it makes no difference. All right? So we need that condenser fan motor running to be able to release the heat from the refrigerant, and by doing so, we're going to have that refrigerant go back to what it likes to be, is that liquid state. Okay, and it's also staying in a liquid state because of the pressure. So we have that pressure-temperature relationship. The metering device is going to restrict the flow of liquid refrigerant. Okay, if we were just to have all this liquid refrigerant pumping through into the evaporator, well, it's just going to continue to stay in a liquid state. So what we need is some type of restriction. We need something to stop all of this liquid refrigerant from getting to the evaporator. By doing so, by causing that little bit of a restriction, that refrigerant now all of a sudden has a chance to flash, or to sort of flash off and become partial vapor, partial liquid, and it also drops the pressure. By doing so, now all of a sudden we get to absorb more heat by traveling through the evaporator. So we have a reciprocating compressor, provides both the suction and compression, operates using a back and forth motion. All right, so we just saw the reciprocating compressor really in motion. Just have the piston goes up and down, compressing everything. All right, and this is just a typical reciprocating compressor. Okay, something you would see usually under in your fridge. Small little appliances are going to have this type of compressor. The reason being it's fairly cheap to make, and so they'll throw these guys into those different applications. Once we start getting into really high-end units, especially for residential, or even like mini splits, inverter technology starts to take place, we're going to start to see different types of equipment.
Air conditioning compressor is a refrigerant vapor pump. In a reciprocating compressor, a piston slides up and down in a cylinder. The downward movement produces suction, and the upward movement produces high pressure. Reed valves are normally used as check valves. These regulate the flow of refrigerant in only one direction through the system. The inlet reed valve only lets refrigerant into the cylinder, and the outlet reed valve only lets refrigerant out of the cylinder. In this way, the piston and reed valves move the refrigerant through the compressor and the rest of the air conditioning system.
So you just saw a little bit of an animation there on how the reciprocating compressor works. So what we have here now is a scroll compressor. Okay, a little bit different of a design. You can see that immediately just from the outside of the unit. It's sort of almost looks like a cylindrical type thing instead of like a small squashed pancake, pumpkin thing, whatever you want to call it. So this guy, he operates on a different premise. We've got some plates up at the top of this unit that are actually going to spin amongst themselves, and they're going to push the refrigerant through. So I've got a little short video on how a scroll compressor operates. These are really great. The reason being is if by chance we get liquid refrigerant coming back to the compressor, compressors don't like anything liquid, all right? It can't compress the liquid. So we may have some failures, we may have some breakage, that sort of thing if liquid came back to a reciprocating compressor. With a scroll, just by the way it's designed, if we were to get some liquid refrigerant coming back, it's not going to damage it inherently just by the way it's designed. So these are really forgiving in that situation. I still don't recommend running it in any liquid refrigerant in there, but it is a little more forgiving.
A scroll compressor is also known as a scroll pump and consists of a shell with an in and an outlet. The lower part of the shell contains the lubricant, which is used, for example, to lubricate the plane bearings. A motor sets an Archimedean scroll, which is found in the upper part of the shell, in motion. The scroll housing has an inlet, as well as a discharge port, and a fixed scroll. Here, the scroll housing is made transparent. The scroll housing has a base plate. The fixed scroll is attached to the underside of this base plate. For better visibility, only the moving scroll with its base plate and the fixed scroll are now being displayed. The gas is absorbed in the forming chambers and transported to the center of the scroll set. As the rotation progresses, the chambers become much smaller, so that the gas is compressed within the compressor. Therefore, this type of compression is called internal compression. In the middle of the scroll housing, which is shown here in green, is a discharge port, through which the compressed gas can escape. Normally, there is also a check valve. Today, there are several compressor designs. On the one hand, the movable scroll can move with an extremely small distance to the other scroll. The scrolls therefore do not touch each other. On the other hand, there are also designs in which the scrolls are in contact. Such scroll compressors usually have a better seal, and thus, a higher efficiency. Axial sealing can also be designed in various ways. One possibility is the use of a floating tip seal. These are present on both scrolls and are pressed against the base plates by gas pressure. In this animation, the upper base plate is not shown. Scroll compressors are used in air conditioning systems and heat pumps. When used in cars, they are known as scroll-type superchargers. The small number of moving components results in a high level of operational reliability. Due to their special design, scroll compressors are also highly efficient. In addition, noise emission of scroll compressors is quite low.
So that was just another animation illustrating how scroll compressors work. That's what we're really going to see a lot of in the industry. Just that's how the design's going. They're really quiet too when you get a really nice one. They used to actually put like little cloth blankets over the tops of some of these compressors just to really dampen the sound on them because they got really annoying. So they've come a long way. You can literally stand right next to a compressor running nowadays and not even hear that thing run. So we've got the oil separation. All right. Purpose of the oil is to lubricate the compressor's mechanical parts. We're going to lubricate the motor bearings. We have moving parts, metal on metal. All right. We want to be able to lubricate these two. We're going to put just a thin film on them just to make sure that we're not scratching away at the two surfaces. The compressor, when you purchase it, it's already going to have oil all inside of it. Same thing with the condenser, the oil's already inside the compressor. So we don't have to change the oil on it like we do on our vehicles. It's just there to run for the life of the system. That oil, what does happen though, is that it starts to travel. Oil likes heat, all right? It likes warmth. And so what ends up happening is during the winter time, that oil starts to migrate into the home where it's nice and warm. So that oil just starts to make its way through the piping into your home. Come springtime, not all that oil is trapped inside your home. If you go to fire up your system, your compressor may not have oil in there, and it would have metal on metal friction, which would lead to premature failure. So to combat this, the engineers designed what's called a belly band, and what ends up happening is it's a small little heater that's put onto the base of your compressor that keeps that compressor just nice and toasty enough for that oil to want to stay there and not migrate to other places. All right. Sometimes if you run refrigerant lines and there's too many bends or kinks, or the air conditioning system is above the compressor or even below drastically, we may have these things called oil traps, where the oil just gets stuck into the line and they just can't go anywhere. If that happens, we may also burn out the compressor, or we may not even have a refrigerant flow because we have oil just gunking up the lines. There's oil separators. They contain baffles or screens to collect oil. So if we're talking about larger commercialized systems, we may have something like this in there. Okay, it's going to prevent the oil from interfering with the operation, and it's placed between the compressor exhaust and the condenser. Usually on residential systems, you're not going to find an oil separator. But basically what ends up happening is oil and refrigerant mixture from the compressor. So oil and the refrigerant, they really like to bind together, okay? It's like just hand in hand, they're connected. And as the refrigerant flows through your piping, so does the oil. So you get a thin coat of oil all along all your piping inside of your refrigeration system. And so what this device does, it's going to tear away the bond between the two. And so the oil and the refrigerant mixture are going to come down this shaft. What ends up happening is the refrigerant wants to travel upwards through the little helical area, and then it's just going to travel on down the line. The oil is then going to want to just drip and condense at the bottom here, and then that oil is just going to return back to the compressor. Okay. The condenser. All right, it's the compressor discharges high pressure, high temperature vapor. The vapor travels through a discharge line to the condenser. Condenser changes all vapor into a liquid, removing its latent heat. So here we are. We talked about latent heat a few chapters ago. We're trying to remove that heat that we can't see, we can't measure, but we know that it exists. All right. How do we know that we're removing this latent heat? Easy. We're going to go to our air conditioning system, our evaporator that sits above or below the furnace, and we're going to listen for water. All right, if water is dripping out of our air conditioning system, we know it's operating. Why? All right, we've got hot, warm air coming across a 55-degree evaporator coil. That temperature difference is going to cause the air and the moisture inside of it to start to condense. Okay, it's like taking that pop can out of your fridge on a hot summer day and leaving it on your countertop or your table. We've got that heat that is being absorbed by that pop can. We've got heat that's being absorbed into the refrigerant via the process, and we've got this moisture. All right, our dew point is reached because we're dropping our temperature, and so that moisture starts to condense. All right, now we're removing latent heat. We're turning that vapor into liquid, and so we're removing the latent heat as well as the sensible heat. Okay. One of the things here is the condenser subcools the liquid, removing some sensible heat. Subcooling. All right, that's actually really important to know. The reason being is we want to cool the liquid below the temperature where it condenses, okay? So let's just say we have a temperature of 100, okay, for the liquid. I'm just making up a number here, all right? That's the point where it condenses, okay? That's our saturated vapor. It condenses, now it's at 100 degrees. If I have 110 degrees, okay, I'm sorry, it would actually be below that, so it'd be 90 degrees. So if I have 90 degrees, I have 10-degree heat difference between the 100 to the 90, all right? So what that means is I would have to increase the temperature from 90 back to 100 to get to the point where I would turn into a vapor. This is critical because certain systems are going to require a certain amount of subcooling to ensure that we have enough refrigerant flow. All right, we want to be, I guess, what's the best way of putting it? We want to ensure that our refrigerant doesn't turn into a vapor before it gets to the metering device. Okay, we do this by measuring our subcooling. The opposite of that subcooling is superheat. Okay, if I have 70 degrees and now all of a sudden, and we're talking about a vapor at this point, my saturation point is 70. Now all of a sudden I'm at 80. Well, I have 10 degrees of superheat. All right, why is that critical? Well, I have a 10-degree buffer before my vapor will turn into a liquid, and by knowing my superheat, I'll know that I have this little buffer, and so that refrigerant, as it flows through the evaporator, as long as I have 10 degrees of superheat, I know I'm not going to get liquid forming before it goes into the compressor. So when we charge our systems, we want to make sure that we have a superheat. Usually it's between 10 and 12 degrees for most systems. That is going to help ensure that we don't have liquid going into the compressor. So subcooling, that's for our metering device, specifically a TXV. We're going to talk about TXVs in a little bit. And then we've got our superheat, all right? Superheat, that's just to make sure that we don't get liquid going into the compressor.
In a fixed volume, such as a condenser, the relationship of pressure, temperature, and heat are shown to be dependent on one another. When a refrigeration system is at rest, the pressure in the condenser is lower than when the compressor is operating. A lower, moderate pressure corresponds with a lower, moderate temperature, low pressure, and low temperature. At this point, the condenser is not expelling heat into ambient air. The condenser and ambient air are at temperature equilibrium, and no heat is exchanging between them. When the compressor begins pumping, condenser pressure increases. According to the combined gas law, in a fixed volume, such as a condenser, increased pressure leads to increased temperature, rising pressure and rising temperature. The rise in condenser temperature creates a temperature difference between the condenser and ambient air, and heat begins to flow out of the condenser's refrigerant and into ambient air. The greater the temperature difference, the greater the heat flow. Eventually, operation stabilizes. In the unchanging volume of a condenser, pressure is equal throughout. However, temperature differences exist. Once enough heat flows from the refrigerant into ambient air, the condenser's refrigerant vapor condenses into liquid. This occurs at a steady rate based on the vapor being pumped into the condenser.
So just
A fixed volume.
Let me pause this here. Okay. So this is actually really good to know. They started talking about ambient. Okay. Right now it's 90 degrees. Everything is, complacent. But this guy was reading 95 degrees a little bit ago. As you notice, the refrigerant, I think, was reading about 180 degrees here. And then as it traveled through, the heat's being expelled and the temperature starts to drop. That's important, all right? Why is it important? Because we need to have a differential in temperature. I need to have a difference in temperature of the vapor coming, the vapor coming out of the compressor versus the ambient conditions. If I were to take, all right, this refrigerant, 180 degrees, and I put it into a room that's 80 degrees, I'm not going to have very much heat transfer. Why? Because we have this equilibrium between the two. We have 180 degrees, there isn't much difference. We're really just going to keep cooking our system. But if I have 180 degrees, and that 180 degree difference to, let's just say, a 0 ambient temperature, well, now all of a sudden that heat's going to want to really leave very quickly because of that huge difference. So that's why places like Arizona, Nevada, they have issues with their refrigeration systems because the temperature outside gets so hot that the compressor really has to struggle a lot to get rid of all that heat. One way of being able to dissipate heat quickly, and what they're starting to do is they're trying to make the condenser units bigger, all right? So we have a same volume unit or a cooling capacity, so we'll say a 3-ton unit. Well, the 3-ton unit, when it gets really energy efficient, it's almost twice or 3 times the size of a traditional unit. And the reason being is, if I have a larger surface area, I can expel more heat without really adding more refrigerant or changing any other dynamics. And so that's what the manufacturers are starting to do. And so we've got a picture here of a traditional condensing system, or outdoor condensing system. All right, we've got air that travels, you know, through the grates on the sides, you know, and then it comes upwards, all right? And as that air comes upwards, it absorbs the heat that was trapped in all these little tubes that are inside here, and then it expels the heat upwards. So we don't want to put anything on top of our units when they're running, all right? The reason being, all of our heat transfer is happening through the top where the condenser fan motor spins. So that's critical to understand. Sometimes people put these under decks, all right? Well, I'm not getting a good heat transfer rate because I've got a deck over the top of it, okay? The other thing too is because we've got this air sucking motion coming in through the sides, we get things that get stuck inside the coils, all right? The coils are just these little fins. Sometimes they're called spine fin coils, especially on American Standard Train. They're like these little, I guess, like finger prickly looking things, and they're really great at dissipating heat. The problem is they get full of cottonwood, different like grass clippings, anything else associated in the yard, and they start to plug up the fins of the units. If the fins get plugged up, we get less air flowing through, less heat transfer, and that leads to problems. All right, so we want to make sure that these guys are clean all the way around, all season long. Sometimes it's just hard to do, especially with cottonwood happening. It's usually a good thing for the HVAC industry, and the reason being it's job security. Cottonwood trees, they're just going to drop all their little fluffies around, they're going to get sucked up into the AC systems, and then us HVAC technicians are going to come in and clean it out. So, all right, so this would be considered an air-cooled condenser. So we're using air to just naturally pass across the coils to release the heat from the refrigerant. We also have water-cooled condensers. All right, we're going to use water to cool them to remove the heat. One example, you may have not noticed it, but retention ponds in like mini malls or in what are those, like commercial settings, industrial parks, that sort of thing, you'll see a fountain just all of a sudden spraying in the middle, and you're just like, oh, wow, that's really cool, that's pretty. That's actually an engineering design. What they're doing is they've got pipes running through that little lake at the bottom there, all right? And what's happening is they're using that little sprinkler system to dissipate the heat, all right? As that sprinkler starts to travel upwards, it releases the heat that's at the bottom of the lake into the air, and it's just naturally cooling off the buildings that are attached via that refrigeration system. So there's really a point to those, not just to make them look cool. So we've got a couple of other condensers here. The one on the left, this is going to be more or less a refrigerant or a refrigeration system. So we're going to be talking about like a walk-in cooler, a flower cooler, a beer cooler, something along those lines. We're keeping something colder than what we like in our own home. So we're talking about 50 degrees, 70 or 60, 40, 30, 20, could even be a freezer. So this is the type of system setup that we have. We've got our evaporator over here. I'm sorry, this would actually be our condenser. So we have our condenser, we've got our fans over here, and then we've got a scroll compressor sitting right there. We have just the controls for it all. It's going to tell the system when to turn on, when to turn off, and so forth. Hard to see here, but we've got a filter dryer. We'll cover that in a second. And then we've got a little sight glass. Sight glass is used for charging the system. You basically peek through the sight glass and it'll actually tell you if we have refrigerant flowing through. You can see a difference between the liquid and the vapor refrigerant. So this is on the liquid line, so we would not want to see any bubbles or anything like that. So it's just helpful for charging. The problem with them is they tend to leak, so they're really it's just a matter of time before we have to replace them. And then back here it looks like we have an accumulator and possibly an oil separator. So off to the right, what we've got here is a Mitsubishi condensing unit. All right, a little bit of a different design than the traditional system in the back here, but it performs the same exact. The nice thing about these is that they actually can ramp up and ramp down, which means that if I have a cooling demand of 12,000 BTUs, but let's just say it's a sort of a lukewarm type of day where it's only maybe like 75, but I want a little bit of cooling on a traditional system, I'm going to get all 12,000 BTUs for that space. The Mitsubishi, it's nice because it'll actually ramp up or ramp down, giving you just a little bit of cooling when you need it. So it's like driving cruise control, right? We're traveling 55 miles an hour down the street. All of a sudden we hit a hill. We need a little bit of gas to get up over that hill to maintain our speed. We then get to the top of the hill. We need to go down. We need to let off the gas a little bit to maintain our speed. So that's the nice thing about these guys. All right. So it's called inverter technology. Really cool stuff, and that's basically what's happening to our industry. Everything is going to go to this way. All right. Really energy efficient. A little expensive, but worth it. So, liquid receiver, storage tank for liquid refrigerant. That actually if I back up here, this looks like a receiver here. I said separator. So the liquid receiver is a storage tank for liquid refrigerant. It allows the charge to be less critical. Holds most of the refrigerant charge for system servicing. So if we go back really quick, all right, critical charge, what's that? So this is a very small system in comparison to this, okay? We're talking about maybe a ton, half a ton, 3/4 of a ton, something like that. We're cooling a very small space. We're talking about a reach-in cooler, not really that large, so you don't need very much refrigerant going through here. Now what ends up happening is, as the temperature outside decreases, I don't need as much refrigerant in my system to maintain the temperature, because the natural ambient temperature outside is keeping things nice and cold. So what ends up happening is, if I left the system alone with the refrigerant charge in there, I would have to come back every couple of weeks, or weather depending, to adjust the charge in my system. I can put an accumulator in here, or a storage tank, or a liquid receiver, and what's going to happen is all that refrigerant is just going to come inside here. It's going to collect in this reservoir, and then it's just going to come out as needed. All right. So it's really nice to have. Prevents liquid refrigerant from overloading the system. Okay. This is just a vertical, horizontal illustration there between the two. So we have the liquid line. The liquid line carries liquid refrigerant to a metering device. Okay. Usually it's made of copper. I know that there's been some talk of using aluminum line sets. The line sets are what we use to connect our condenser to our evaporator. The line set is 2 lines. They come insulated, or at least one does. And we're going to carry the vapor refrigerant to the evaporator. We're going to carry liquid refrigerant, vapor refrigerant to the condenser, and liquid refrigerant to the evaporator. The liquid line is the smaller of the lines. Okay. Like I said, there was some talk of people using aluminum. I don't like aluminum line sets. I would stay away from them. I've seen videos of them exploding. So if anybody suggests to put anything on to carry refrigerants other than copper or a stainless steel, yeah, I would run away quickly. So how do we connect copper? We connect them via brazing or flared fittings. Brazing, we'll cover that in a couple chapters, but basically we apply heat to the copper surfaces. As we apply the heat, we add a filler material which melts and fills in the gap between the two copper fittings. Okay. Flare fittings is just a flare connection. Basically what happens, we have this cone shape that fits over a convex shape, and we tighten them down with a nut. All right. Real good setup. We use flare fittings in mini splits. Smaller diameter than the suction line. So the liquid line, because of the amount of refrigerant that the capacity that it holds in a liquid state, I don't need as much volume, and so I have a smaller line. Okay. It may be in contact with the suction line. It subcools liquid line refrigerant, reduces chances of flash gas in the liquid line, and superheats suction line refrigerant. So those are reasons why we would have the liquid line in contact. It's not always the case, but there are reasons for it. So we want to keep our refrigerant clean. All right. Sometimes impurities, things like that, fall into the refrigerant. Sometimes there's a little bit of air that gets in there. So we want to keep the refrigerant as clean as possible. So we put a filter in there. Okay. It's really good to put one in every single time you open up the system. So if you're doing a repair, I'm going to replace the filter dryer. Okay. Reason being, that filter dryer gets plugged up. We open the system up. Now it's exposed to atmospheric conditions again. It may plug it up some more, and so we don't know what happens. So we're just going to go ahead. We're going to put in a new unit. Okay. It removes moisture from the refrigerant. Moisture might otherwise freeze and cause obstructions. That's another thing. If we had a little bit of water inside of our system, we've got this refrigerant that's running really cold inside of our space, and all of a sudden it hits some water. Well, now we get a little chunk of ice floating through our system. That's definitely going to plug something up. Okay. We talked about this a little bit ago. Moisture can form sludge and acid. Absolutely. We want to make sure that we don't have any acid floating around in our system. So here we go. Just 2 illustrations, or 2 pipes running to our unit. Which one's the liquid line? Well, hopefully you guys can see it, but this liquid line's a smaller one. All right. We've got a filter dryer connected to our liquid line, and we're running over to our compressor. All right. The larger one is our vapor line. The vapor line is also going to be covered with insulation, so that's another way to know that we've got our vapor. Why do we have insulation? Well, our refrigerant is traveling from inside. We've absorbed heat from the evaporator. I don't want to absorb any more heat. Okay, I don't want to absorb any more heat traveling down here, because as I travel further, there's still heat being the pipe's exposed to atmospheric conditions, there's still heat available and the refrigerant is going to still try to absorb it. And by doing so, we may start to form condensation around the area. All right, we remove the heat from the air. That air lowers the temperature. It can't hold as much moisture. And now all of a sudden, we start to get condensation forming on our line. So we may develop leaks or dripping from our pipes, and we don't want that, especially if they're running behind drywall or anything like that. So insulation is critical on the vapor line. If we're running mini splits, not to overload you guys, but the refrigeration cycle can actually go in reverse. And by doing so, we now can heat a home, right? We take the heat from the outside, we suck it in, we bring it to the inside, and we heat our home. So in that case, both the lines are going to be insulated. So a metering device, it controls the flow of refrigerant into the evaporator, okay? Reduces liquid refrigerant from a high pressure to a low pressure, and it's located between the liquid line and the evaporator. Just a couple other names: refrigerant control, refrigerant flow control. Never heard of those, to be honest. Usually people are going to go by the type of name that exists for that metering device. So if I'm talking about a TXV, I'm going to refer to the metering device as a TXV. I'm going to call it worst case a metering device, or it'll be a piston, it'll be a cap tube. So refrigerant control, not in my book. So there's several different types of metering devices. So I just mentioned the TXV. So we've got the thermostatic expansion valve. All right. So we've got the inlet. We've got our liquid refrigerant coming into this guy, and inside here there's a little diaphragm and a pin, and basically it's going to allow a certain amount of refrigerant flow to come through this outlet. This sensing bulb connects to the line, and it's going to sense or determine how much superheat is being absorbed, how much heat is being absorbed by the evaporator, and based on how much heat is being absorbed, it's going to open and close, allowing more refrigerant to flow through. All right. So we have a fixed orifice. Fixed orifice is real simple. It's just a pinhole, and we're going to allow refrigerant to flow through the little pinhole. Just a little pinhole restriction isn't just enough to allow the refrigerant to slow down. Capillary tube is just almost looks just like this. All right. It's just a very small, thin copper tube, and just by the whole sheer nature of how long that tube is, causes the refrigerant to really slow down and drop temperature. So we talked about TXV. AXV, very similar to the TXV. It used to be more popular, but you're not going to see really the TXV so much. It operated on a completely different premise. To be honest, it's almost the same exact thing. And then we've got the electronic expansion valve, the EEV. Okay. Then we have the floats, low side, high side float. Basically, there's just going to be a reservoir, and the float's just going to open and close depending on how much refrigerant is needed on demand. All right. So this is just an example of a capillary tube. I've got my compressor right here, and I've got this coil of tubing right here. All right, so my refrigerant flows through this tube, and you can see how much of a difference in size it is in thickness here. You know, maybe like a 3/8 comes in, and then all of a sudden it drops down into this really tiny fine tube, you know, maybe from 3/8 to 1/8, and that just causes that whole reactionary process to go through. So this would be a piston. So piston would sit inside here, and what the piston does is it's just like a little type of piece of metal with a small hole drilled inside of it, and that's just going to allow enough of a restriction for the refrigerant. Depending on the application you have, you can actually replace the piston inside of here to allow more or less refrigerant to flow through. Here we have a TXV hooked up, and so we've got the sensing bulb right here, the TXV, getting ready to do its thing. And then up here, we just have another line connected to it, and that's just helping the TXV really find a equilibrium to know how it's operating on both sides of the system. Not all of them are going to have these two lines connected to it, but just know it exists. Real simple to identify, especially with this little head and this little cap right here. On most of the TXVs, you can actually take this cap off, and you can turn the valve inside to open or to release more refrigerant, or to close the amount of refrigerant coming through. 9 times out of 10, you never touch the TXV. You never have to adjust it. Very rarely do you ever have to go in there and mess around with it at all. And then we have the EEV or LEV, and basically what this is, it's a little stepper motor. Inside here, we've just got this little small, I guess, like a little seat inside. And basically these things are really nice because they can go from, I think, I want to say something like 2,000 different steps inside here, which means that they can open up all the way, they can close all the way, or they can open incrementally about 2,000 times in between. So depending on how much refrigerant flow you need through, it's going to open and close depending on the demand. All right. These are all electronically controlled, so there is no sensing bulb or anything like that. It's just all digital. So the process of evaporation. Warm air passes between evaporator fins. Heat is absorbed by liquid refrigerant. Liquid boils into a vapor. Temperature of air flowing over evaporator becomes increasingly colder. Cold air cools the conditioned area. I haven't really said it specifically like this, but we've been working through the entire chapter to get to this point, okay? Understanding the whole process of evaporation. So this is an evaporator, okay? I'm going to have my refrigerant come in on one side. It's going to fill up these fins, these coils, make them nice and cold. The air is going to come across it. And it's going to blow across the nice cold coils. Heat gets absorbed into the refrigerant, and then it comes out and travels back to the condenser to repeat the process. There's tons of little tubes, so if we didn't pull out all the moisture out of their system, we're going to have some ice that can potentially build up in there. If we don't have a filter dry in there, we may get some impurities that plug up these little holes, and that's the last thing we want, because if we plug up a hole, we're not going to get refrigerant flowing through. This is another form of evaporator. This one you're going to find more in a commercial type of setting, walk-in cooler, flower cooler, that sort of thing. All right, just that type of design. This is called an A coil, all right, for the shape of the letter A. And what ends up happening is this is going to sit usually on top of your furnace. As it sits on top, the air is going to blow through both sides of the furnace, and it's going to absorb any heat that's there. So we've got these little grills, these little radiator passages that the air is going to travel through. This is considered an N coil. All right, Carrier likes it. I personally hate it. So what ends up happening is we've got air that's going to travel through this way, just like it does an A coil, because that's what this shape is. But Carrier decided that that's not enough, and we need to put another little leg over here, so we get air that travels through this side as well. So we have air that literally travels through 3 different sections. Personally, I see more of an air restriction with this type of coil than I do it being a positive matter, so I really don't like to use them, but if you're installing Carrier products, this is what you're going to get. We see our TXV right up here, going to control the refrigerant. At the bottom here, I didn't mention, this is our condensate. All right, we have a little drain pan at the bottom of these guys. Same thing with here, got a drain pan. As the water or the air comes up through the bottom, it hits the sides of the coil, the water collects on the fins, and it slowly drips down until it gets to the pan. Once it hits the pan, it collects and starts to come out this little drain hole, which gets connected to your condensate drain line. The reason we have two little holes here, couple reasons. If my condensate drain gets plugged up for whatever reason with this hole, I've got a backup. I can have another line for my condensate that connects to here. So as my water level fills, my primary doesn't drain, well, my secondary should take over that load. I can also put a sensor inside of here so that if my primary gets backed up and my condensate pan starts to fill up, well, the switch will tell the air conditioner to stop operating. And when it stops operating, I'm going to get no more water buildup. All right. As a homeowner, I would then know that I've got no air conditioning going on, and I would have a technician come in to figure out why. A couple other evaporators. These are for the mini split line. We've got a wall-mounted unit here. You're going to really start to see a lot of these start coming into the market nowadays. Got little fan or blower motor inside of here. It's going to suck air through the top, and the air is going to come out through the side. So it's almost like a one-stop shop with this guy. I don't need a furnace. This is going to provide me both heating and cooling, as well as all these other guys. So that's a wall-mounted unit. This is a floor-mounted unit, they call it. This guy sits almost on the floor level, but it mimics the old-school radiators. Air comes in through the bottom, and it gets shot out through the top. All these units have vanes that do move, so we can direct the airflow in the direction that we want it, left and right, up and down. And then we also have the sealing cassette here. This is actually going to sit inside your ceiling. It's going to be nice and flush. So all you see is the grill aspect. And then the air gets sucked in through the back, goes through the coil that's inside here, and gets passed through the vane at the front. So we have an accumulator, okay? The accumulator captures liquid refrigerant in the suction line. Liquid can damage the compressor. We've talked about that. We don't want the liquid hitting the compressor because it's going to damage the reciprocating compressor. The scroll is capable of handling it, but we still don't want that liquid refrigerant getting back there. The reason being, the liquid doesn't compress, we're going to potentially break something. All right, how do we know we have enough? We know that we don't have liquid refrigerant coming back to the compressor. Well, we have enough superheat. Okay, we're 10 to 12 degrees above our saturation point. Okay, our boiling point for that vapor. We know that we're going to be okay. So an accumulator, it's not required in most small systems. You're not going to really see this on the residential side. The reason being is it's not needed. Suction line, all right. I showed you that bigger line in that illustration. It's going to carry the refrigerant vapor from the evaporator to the compressor. And it carries a superheated vapor with minimal flow resistance. So as the refrigerant turns into a vapor, it's just going to naturally carry through. There is no restriction, there isn't anything, just passing on by. It should slope from evaporator down to compressor. Not entirely true, all right? And the reason they say that is because they want that oil to travel back to the compressor. Sometimes it's impossible, depending on how you have your lines run and the design of the building and so forth. The evaporator may be below the compressor, or below the compressor. It may be above the compressor. So getting a slope to it, it's hard to do. As long as we don't have any like U-shaped traps or anything like that in our lines, most systems are going to be able to handle that. Okay. Suction line is made of copper. We talked about that. We don't want any aluminum lines. Stainless steel is okay too, but that's really for the commercial setting, especially dealing with like ammonia or something like that. And the tubing is insulated to prevent condensation and the absorption of heat in unconditioned spaces. So, like I said, we want to keep insulation on there. If the insulation is broken, we're going to put new insulation on there. Okay. Refrigerant is superheated above its saturation point. Superheated, but feels cool. Refrigerant is interesting animal. You know, we talked about how the boiling point of 410A is -60. Well, yeah, it's going to feel cool. Even though the saturation point is, you know, let's just say on a specific pressure, it's 60 psi, well, it's still going to feel cool to us because it's really operating at 30 degrees. So, think green, insulate suction line. So we don't want any condensation on the suction line, vapor taking heat from spaces not intended to be conditioned, and system bearing a heavier load than it should. All these things are true if we don't have insulation on there. And then we also have a suction line filter dryer. So if we were to have, let's just say, a burnout on our system, we're going to also put in a suction line filter dryer. All right, it's going to protect the system from acid and contaminants. So let's just say the previous technician came in there, screwed up our system, we got a burnout. Well, we got to remove all that, those impurities out of our system. Okay, so we're going to replace our compressor because our compressor is bad, and then we're going to flush it. So we're going to use a chemical cleaner that goes inside there. It sort of scrubs the walls, removes any oil, any acid that's inside there, and then we're going to put a suction line filter dryer on there. It even tells you right here, high acid capacity. We're trying to remove the acid out of the system to protect our new compressor, and we're probably going to put 2 or 3 of these on there to make sure that we have no more acid in our system. So it's used temporarily. Okay, we're just really cleaning out the system to make sure we don't have any acid in there. So, and that's it, gents. We covered basic refrigeration today.